And hello, this is the third lecture for chapter 4. And in this lecture, we are going to be covering acid-base reactions. So the last lecture was precipitation. The next lecture will be oxidation reduction. In this one, we're just going to be talking about acid-base, and we'll finish the lecture with a few examples of the kinds of problems that you'll be asked to solve. All right, so we measure the acidity or alkalinity of a solution or a material on the pH scale. So the pH scale actually stands for potential of hydrogen. And let me get that written down for you guys. So pH equals potential of hydrogen. And what that really means is it's going to be the concentration of our hydrogen ions. So these brackets that I'm putting on here are a way of indicating that you're talking about the concentration of that material. So if you were talking about ADP in the human body and you were talking about the concentration, you could say concentration ATP. So pH is a measurement of the concentration of hydrogen ions. We know that hydrogen ions are also called protons. So just keep that in mind because we're going to be talking about things that are protonated and deprotonated in a couple slides. Okay, so the pH scale is an inverse scale, so it's the negative log of the concentration of hydrogen ions. So because we have this negative here, it is going to be like somewhat counterintuitive. So the more hydrogen ions you have, the lower the pH. So here we have a battery, which is a pH of 0, and that is going to be a very acidic thing. Stomach acid has a pH of about 1. Lemon, your citrus fruits are going to be between 2 and 3. And on we go until we get to water, which has a pH of 7. Now, in water, that neutral pH of 7, lets us know that our hydrogen ion concentration is equal to our base concentration or hydroxide concentration. And for those of you who are going on to take Chem 125 at SMCC or the second semester of chemistry at any other school, you will spend quite a bit of time in Chem 2 looking at acids and bases and how they behave in water. So this chapter is really an introduction to acid-base reactions, and we're going to narrow our scope to some pretty specific parameters, which I'll talk about as we continue the lecture. Now here we have bleach and drain cleaner at the opposite end of our pH scale, and that's going to be a very, very low concentration of hydrogen ions, higher concentration of hydroxide. So acidic, your concentration of hydrogen ions is high. Here, concentration of hydrogen ions is low. And because if we think of neutral as being water, we have this nice kind of balance between our hydrogen and our hydroxides. So in an acidic compound, the base is going to be low while the acid is high. And in our alkali compounds or materials, you're going to have a high level of OH. So all of the reactions that we're studying in this chapter are taking place in water, and as you could see from that last slide, there is a direct relationship between hydrogen ions and hydroxide and the pH scale where we measure acidity and alkalinity of something. So here we have 3 compounds that are all kind of based on the water molecule, are very similar, and because everything that we're doing is in solution, I just wanted to kind of talk about one of the qualities of water that makes it so interesting and allows for so many dynamic reactions to take place. So here we have our water molecule, and that is going to be a pH, of 7. So it's neutral. Now, water can act as an acid. And when it acts as an acid, it is going to lose a hydrogen and become hydroxide. So the way that we will define acids and bases in this class, there are a few definitions for acids and bases. In this class, we're going to talk about them on the Bronsted-Lowry definition. So in the Bronsted-Lowry definition of acids and base, an acid is going to be a proton donor. And a base is going to be a proton acceptor. So when we have water moving from H2O to our hydroxide, notice we've lost this hydrogen. Right? Where has it gone? It's gone into solution. So in losing a hydrogen and giving it up to its environment, water has acted as an acid, right? A proton donor. And now it is the negatively charged hydroxide. If water instead went the other way, which it can do, and behaved as a base, it would pick up, right? So this is lost. Now it's adding a hydrogen from the solution, and it forms H3O. So this is, let me let those marks go away. So here we have our neutral water molecule in the middle here. Then we have our hydroxide ion, which is negatively charged, and over here we have the hydronium ion. Now in that chapter 4 overview, I've added a cool PhET simulation that looks at the concentration of hydronium, water, and hydroxide in the presence of acids and bases. So you might want to just take a look at that so you can start to see how there's this dynamic equilibrium that exists as water is introduced to other species. Because again, we're interested in reactions that are taking place in water. Okay, so here's an example of acid-base chemistry. And I chose this because I think almost every reaction that you are asked to analyze in this class is going to have a base that has a hydroxide on it. So it's really easy to identify. However, there is this one exception with ammonia. And ammonia will take on an additional hydrogen to form the ammonium ion. We know that from our polyatomic list. We've been working with this particular chemical for quite a while. But now we can have this new understanding that the difference between our NH3 and our NH4 is the addition of a hydrogen ion, a proton. So here we have our NH3. Now that has become protonated. It has taken on a proton and as such has behaved as a base. So in this reaction we have our ammonia and our water. And the water is acting as an acid. It is donating a proton to our ammonia to form the ammonium ion and hydroxide. So these terms here, conjugate acid and conjugate base, you are not expected to know for this class. That's kind of a lead-in to Chem 2. So in this class, we really just kind of look at our chemical reactions as if they were a one-way street going from reactant to product. Chem 2 is all about how every reaction reaches a dynamic equilibrium, and because of that, our reaction arrows, as you advance in chemistry, stop being one-way streets and instead reflect that equilibrium, that balance that is achieved. So when you're assessing acid-base reactions, what you're going to do is called follow the proton. So in order for an acid-base reaction to occur, there has to be a proton transfer. So if you were looking at a chemical reaction, you were asked if it was an acid-base reaction, there was no hydrogen. you can be pretty confident it's not an acid base. So here we have NH3 becoming NH4. What's the difference between those species? It's taken on a proton, right? What's the difference between my water and my hydroxide? It's lost a proton. Water's acted like an acid. Now, the reason why we call it a conjugate base is that now this hydroxide is ready to pick up a hydrogen proton from somewhere. So base becomes a conjugate acid, acid becomes a conjugate base, reflecting that two-way street, right? Our ammonium ion is now ready to give up a hydrogen to revert back to ammonia. And in fact, in our solution, this is happening constantly, and this dynamic equilibrium is what we call it, is achieved. So the big takeaway there is follow the proton, pay attention to who has lost a hydrogen and who has gained. And remember, a base gains a hydrogen, an acid loses a hydrogen. Bronsted-Lowry definition of an acid. Okay, so here's the nice little molecular view. So these little like blurbs here, I don't know what you'd even want to call them, wings, I guess, on the molecule are called lone pairs. We don't need to get into that. Just think of that as being electron density around this chlorine atom. So this is our chlorine. Let me get my pencil out. So this is our chlorine and this is our hydrogen. Here we have water. So this is that's oxygen, and here's our hydrogens. Then we have our chlorine ion, and we have H3O, otherwise known as the hydronium ion. So hydrochloric acid loses this hydrogen. That hydrogen goes somewhere. It's not just like free floating in this world. It's going to get picked up by anything that is more basic than our chlorine. So anything that desires or has an affinity for that hydrogen more than the chlorine. And in fact, water does. So it becomes H3O. Water is acting like a base, right? It accepted a hydrogen. Hydrochloric acid, as its name would imply, acted as an acid. This little note here about conjugates, acids, and bases, you don't need to know, but acid-base chemistry is really interesting. We'll finish the lecture with a little spiel about why you should care about acid-base chemistry, so I'll leave that for the end. The suspense. Okay, so we have hydrochloric acid here. This is just from another textbook that I really like to show you how these bonds break in order to form your acid in solution. So when we have HCl, right, what happens is the electrons that are held in this covalent bond, right, we have two non-metals bonded together, it's a covalent bond, but if you look at your periodic table, we know that chlorine is much more electronegative than hydrogen. It has a much stronger pull on that on those electrons than our hydrogen does. So when we're in an aqueous solution, it's quite easy for those electrons to be just donated to chlorine, forming our chlorine ion. And then we have our hydrogen ion. And again, that's going to get picked up in solution by something. The same thing would happen with hydrobromic acid, where this is our hydrogen and this is our Br. And this relationship, the similarity between HCl and HBr, should not surprise you because they are in the same group on the periodic table. Hydriodic acid is also on the same group, so again, not surprising. Then we have some cool additional acids I just threw in here for fun. So nitric acid, we've been talking about that a lot. Here we have our NO3, right? This is our hydrogen, and that bond is going to break. Electrons get donated to our oxygen. Hydrogen is without an electron, so it's just a proton in solution. Again, ready to be picked up. Sulfuric acid is one of our strongest acids. It will readily get rid of one of these hydrogens. It usually tends to hold the second one, although if it's in a very basic solution, it will also lose it. And then last we have our perchloric acid, HClO4, hydrogens being lost. So we're used to seeing these species, right, from our polyatomic ion list. And the reason why we're used to seeing them as ions is that they're very stable, right? So strong acids are very stable without, let me actually, yeah, we're going to redo that. So strong acids can readily give up a proton because they are able to stabilize a negative charge. Right, and we've already kind of seen this with the polyatomic ions. We know that we see them all the time in their ionic form. Now we just have this deeper appreciation that it's because they can readily give up this proton. Okay, so your lab this week is all about titrations, and I think this is a really good way of showing you the kinds of acid-base chemistry that you'll be asked to investigate. So in a titration, we typically have a solution. That's annoying. Okay, so we typically have a solution that is unknown in an Erlenmeyer flask or whatever glassware, and that is called an analyte. So the analyte is whatever you are analyzing, right? So usually the analyte is going to be unknown concentration. Right? So ultimately a titration is trying to figure out what our concentration of our analyte is. In this burette, this is called a burette, you have your titrant. So that is going to be something of known concentration. So you have your unknown concentration and your known concentration. And what you're looking for is this equivalency point. So all acid-base chemistry that you're looking at is basically going to boil down to this HA plus BOH going to H2O plus RBA. So this is an acid plus a base, right? 99% of the bases of the acid-base reactions that you'll be asked to look at are going to involve hydroxide. If it's not hydroxide, it'll be ammonia, right? We keep it pretty simple in this class. So if your acid and your base combining to form water and a salt. All right, so this would apply for that last reaction that we were looking at, or the first one that we looked at, where it was HCl plus NaOH forming water and sodium chloride, right? An ionic salt. So in a titration, you're trying to find the point where all of the H plus, the entire concentration of your hydrogen ions have been neutralized with hydroxide ions. So you have this point where your concentration of hydrogen and your concentration of your hydroxide are equal. And ultimately, when you look at these reactions, you have your hydrogen plus your hydroxide going to water. And this is called a neutralization reaction. So let's say in this reaction, our analyte is going to be a strong acid. All right, and let's just say it's HCl. And our titrant is going to be a strong base, and we'll say that it's NaOH. Now we are adding NaOH just a drop at a time. So burette, the utility of it is you can add very small volumes at a time, and it very precisely measures the amount of volume dispensed. It's going to be added to our beaker, and you can see here that we're starting to get this pink color. So that pink color is from an indicator dye. And an indicator dye is going to be a chemical compound that changes color at a certain pH. So in this case, our indicator dye is phenolphthalein, and it is going to turn pink when it is in a basic solution. So here we would have the endpoint of our reaction, which is the point at which that indicator color stays. So at this point, this solution is going to be just slightly basic. So our endpoint is always just past this equivalency point. And again, our equivalency point is going to be where hydrogen concentration is equal to our hydroxide concentration. That means that we've added, in this example, enough of our NaOH to react completely with every hydrogen that our hydrochloric acid kicked off into solution. So at that point, if all of our hydrogens have reacted with the base that we've added, we have a neutral solution. Okay, so neutralization reactions, when you're studying them, the first thing you have to do is determine what reaction will occur. What does that mean? You need to follow the proton and identify the species acting as an acid and the species acting as a base. Then it's a good idea to write your net ionic equation so you can make sure that the analysis that you've done is correct, that you would have these things breaking apart into their ions so that they can find each other in solution, right? So everything that we've been talking about in this lecture is really just an addition on what we learned about in precipitation reactions. Only in this case, you don't have ions breaking apart and forming a precipitate. Instead, you have ions breaking apart and neutralizing each other to form water, right? Those ions being the proton and the hydroxide. And that should also make sense because we're using strong acids and strong bases, and we know that both of those are strong electrolytes. They're going to dissociate completely in solution. So then you calculate the number of moles of reactants. You determine the limiting reagent. You figure out what you needed to do, and then you convert your unit. So none of this is new. Now we just have a new kind of reaction that we're assessing, and that's a neutralization reaction. All right, so let's go ahead and do a couple problems so we can get some practice. All right, so here we have what volume of a 0.100 molar HCl solution is needed to neutralize 25 milliliters of 0.350 molar NaOH, right? We're working with solutions, lots of molarity and volumes that we're looking at. Okay, so it's good if you read a problem like this and you're like, oh my God, I do not want to do this. One of the best things that you can do, I don't know why I can't change my color, is just to underline the numbers and the species that you're looking at, and that's going to allow you to there we go. That's going to allow you to kind of simplify your problem and start to look at it in a more concrete way than sometimes word problems can feel. Okay, so the very first thing that I like to do in these problems is just figure out what my reaction is, right? And we've already talked about this reaction already, so spoiler alert, you already know. So you have hydrochloric acid plus our sodium hydroxide. Now you look at those two species, you think about everything that we've learned in this chapter, and hopefully should be able to recognize that this is a strong acid, this is a strong base, they're strong electrolytes, they're going to break apart in solution. So just like we saw with precipitation reactions, this isn't necessarily the most fair representation or the clearest representation of our species in solution. So actually what we have here for our reactants can be written like so. So when they dissociate, is there a reaction that can occur? Well, we know that sodium is a type 1A metal. It is not going to form a precipitate. This is not a precipitation reaction. So the sodium is going to stay in solution. The chlorine ion is going to stay in solution, but you bet the hydrogen and hydroxide are going to find each other, and you get H2O. All right, so what's happened? We've had the transfer of a proton. So it is an acid-base reaction. Now, like we also had in precipitation reactions, we have our spectator ions, right? Nothing really happened to our sodium and our chloride. So we could write a net ionic equation here. And, oh, not chlorine. Oh, now I just highlighted it. Ignore the highlighted part. Let's get rid of that. Yeah. There we go. We have our hydrogen and our hydroxide combining to form water. This is a neutralization reaction. Okay, so now we can fully understand what is taking place here. Now we just need to plug our values in and figure it out. So we have our acid, HCl, and it's 0.1 molar. And the question is, what volume? Then for my base, I have NaOH. And I know that I have 0.350 molar. And my volume is 25.0 milliliters. Okay, remember, we're looking at neutralization. And in neutralization, your concentration of hydrogen is going to be equal to your concentration of hydroxide. So what we need to figure out is how much hydroxide do we have, and then how much of our hydrochloric acid do we need to completely neutralize it. So again, we're comparing two different species, so we're keeping this in the realm of moles. So we have our molarity times our volume in liters is going to give us the number of moles of NaOH we have. And I got 0.00875 moles of sodium hydroxide. So now we need to figure out how much of our hydrochloric acid solution do we need. So we're just going to perform stoichiometry using our balanced chemical reaction. So we have a 1-to-1 mole ratio. Oh. And now we're going to use our molarity, right? 0.1 molar means 0.1 moles in 1 liter. So now we can figure out what that volume is, and you're just dividing by a tenth, so move the decimal place 1 to the left. And our answer is 87.5 liters of HCl. What happens when we add that 87.5 liters of HCl? We've added exactly enough hydrogen ion to react entirely with the sodium hydroxide, converting all of our hydroxide to water, creating a neutral solution. All right, let's do another one. So what volume of a 0.5 molar solution neutralized blah, 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 of HBr? Okay, so this is similar, but we do have a different mole ratio. So we have our hydrobromic acid plus our calcium hydroxide. That is going to form CaBr2 plus our 2H2O. So same steps as we've done all along. Write your balanced chemical reaction. CaBr2, definitely going to be in solution. So again, we could reduce this to its simplest ratios to say, yes, this is a neutralization reaction. But unlike our last example where we had no coefficients to keep in mind, now we do. So that's going to be, oh, sorry, I forgot that too. That's going to be important for our stoichiometry. All right, so we're setting up our problem the same way. So for our HBr, I want to figure out how many moles of my hydrogen I have so I know how much hydroxide I need to neutralize it. So for HBr, we have 100 milliliters, otherwise known as 0.1 liters. It is 0.3 molar. So my moles of hydrobromic acid is going to be equal to 0.1 times 0.3. which is going to give me 0.03 moles of HBr. And when you look at this 0.03 moles of HBr, because you have one hydrogen in every molecule of HBr, in 0.03 moles of HBr, you have 0.03 moles of hydrogen ions once it dissociates, and you have 0.03 moles of our bromine once that dissociates. Okay, so this is the amount of hydrogen ion that we have, proceeding from what we got in our stoichiometry, proceeding on with our stoichiometry. Looking at our balanced chemical reaction, we have 2 HBr for every 1 CaOH2. And our concentration is 0.1 liters. Oh, sorry. That is my volume. Our concentration is 0.3 molars, so that is mole in 1 liter. And you get 0.03 liters, otherwise known as 30 milliliters of your CaOH2. So going back to this kind of analysis that we did here, let's just do the same thing for our calcium hydroxide. So remember that calcium hydroxide, if you had 1 mole of calcium hydroxide, that means that you would have 1 mole of calcium and 2 moles of our hydroxide ion. So it's really important when you're looking at these neutralization reactions to start with a balanced chemical equation, right? Because having this 2 here accounts for the fact that you need half as much calcium hydroxide as you need hydrobromic acid. Alternatively, you can just look at the ratios and work things out from there, just knowing that if you have a 2-to-1 ratio of hydroxide to hydrogen, you need half as many moles of your calcium hydroxide, and then proceeding from there. Or you can do stoichiometry, as we have been doing this whole semester. So whatever you get more comfortable with and you can consistently answer questions correctly, go ahead and use it. No qualms there from me. Okay, so now we have one last reaction to analyze, and that is our a mixture of nitric acid and potassium hydroxide. All right, so these two things are mixed, and the question is, what are the ion concentration, or what ion is in excess after the reaction goes to completion? So you have a little bit more complicated of a problem here. But if you look at it, it's really just applying what we've been doing this whole semester, or at least since chapter 3. Right, neutralization reaction. Neutralization reactions, we know, are always looking for that point when your hydrogen ion is equal to your hydroxide ion. So how many hydrogen ions do we have? Well, we need to use our molarity and our volume. So 0.25 molar HNO3 times, or 0.028 liters, is going to give us 0.007 moles of HNO3. In that 0.007 moles of our HNO3, we have 0.007 moles of our hydrogen ion, right? 1-to-1 ratio. Now we have our 0.320 molar KOH times our 0.053 liters, and we get 0.01696 moles of KOH. And in that compound, we know that that will dissociate in water. It's a strong base, it's a strong electrolyte. We get our concentrations of hydrogen and our hydroxide. So the question is, which one runs out and which one do we have excess of? Well, looking at our ratios, we see that it's a 1-to-1 ratio. What do I have less of? I have less hydrogen, which means that my hydroxide is going to be in excess. Well, how much will it be in excess? Well, if I only have 0.07 moles of my hydrogen ion, I only needed 0.07 moles of my hydroxide, 1-to-1 ratio. So that means I can take the total number of moles of my hydroxide that I have, subtract the number of moles of hydroxide that I need to neutralize, and you'll get the total number of moles of hydroxide ion in excess, which is 0.00996. Whew. So this is the number of moles, but the question is, what is the concentration? So after you answer a question, go back, read the question again, make sure you actually gave the right answer. So this would be not a concentration, but just the number of molecules. So in order to convert mole to a concentration, I need to divide by the volume. So I'm just going to round here, 0.001 moles of my hydroxide would be divided by my total volume of solution, right? So that is going to be that 0.028 liters plus my 0.053 liters. All right, make sure that you put that in parentheses so that you're dividing by the sum of those values, and you get 0.123 molar OH. Pretty cool. It's really just a further application of what we've learned thus far, which is very exciting. Okay, speaking of very exciting, I promised that I would just finish this chapter with a reflection or an appreciation for the importance of acid-base reactions. So your body is constantly undergoing an acid-base reaction in the carbonate buffering system, which any of you who are going into the healthcare field will become very familiar with. Interestingly, this exact same reaction is taking place in our oceans. So there's some real similarity between the way that we maintain our pH and the way the ocean maintains her pH. Okay, so in our bicarbonate buffering system, you have the intake of CO2, or in this case with the lungs, the expelling of CO2, although the lungs do get CO2 from the body, right, carried in hemoglobin, and then it's expelled as we breathe out. So that carbon dioxide combines with hydrogen to form H2CO3, which is also known as carbonic acid. Now that is an acid, so it shouldn't surprise us that it can lose a proton and form what is known as the bicarbonate. The bicarbonate ion. Now what's cool about acid-base reactions, and as these arrows are trying to show, is that you have this dynamic equilibrium that's reached. So if you, for instance, have a situation where the pH of your body goes up, you can try to get rid, or your body automatically tries to get rid of those extra protons by expelling more. If the pH goes up, it's shifting equilibrium this way, so your body's going to counter that, and you will produce more CO2, which will increase your respiratory rate. So this bicarbonate buffering system is this dynamic interaction between our kidneys, which expel bicarbonate through urine, and our lungs, which expel CO2 in gas in order to form a dynamic equilibrium through acid-base chemistry that allows us to survive. And when this system goes awry, it is a huge no-no, or hugely detrimental to the human organism, and the same is true for our oceans, as we see in the acidification of our oceans and the death of our coral reefs. Right? It's all connected. Very cool. All right, acid-base chemistry. Check it out, get some practice, enjoy it. The next lecture will be over oxidation reduction reactions.